Um, hey, Neil, I wanted to say thank you for the kind words. You're always so kind. It's one of the reasons I come back and like to do these sessions. Um, I also like to do these because there's a lot of people that I know that are on here. I kind of scanned the screen real quick of people that were here. I didn't get a chance to see all of them, so if I miss you, I apologize. But I just want to give a shout out to Dan Hartman. I saw that Dan was on here. Dan, I always enjoy visiting with you. I hope you come to the Southern Chapter Conference this year. We're going to be over in Little Rock. Um, Casey, I saw you on there, Casey Kraus, arborist with City of Knoxville. And I also saw a hometown person. I saw Jeannie on here, Jeannie Metzger. So Jeannie, thanks for joining. Appreciate it. Jeannie's with, I believe you're still with City of Clayton here in St. Louis as an arborist. So, got some people that I know, a lot of people that I don't know, but that's good because if I have a crowd of people that I don't know, then you all think I'm an expert and I can fool you easily. Those of you that know me know that Skip really doesn't know that much. So but I know enough to be dangerous, I guess. But the one thing I think a lot of people would agree on is that I'm passionate about trees, and I really am. Um, this particular topic, this how trees grow old and fall apart. This is one of those PowerPoints, one of those presentations I've had for a few years now. I did this down in New Orleans at an event they call Tree School down there, about 500 or 600 people that attend a 1 day event. It's pretty cool, and got just a ton of questions afterwards. And every time I do it, it just sparks a lot of discussion and interest. Um, it's even for arborists, I think you're going to see some stuff today that maybe you didn't pay a whole lot of attention to. It's not brand new science. None of this. I am not a researcher. This isn't like new science or some wonderful result of some of my research. Um, I'm a talker. I don't do the research. I just share the knowledge, I guess, kind of like Neil does. So with that, we'll jump into this. I just real quick background. Neil mentioned to you that I am executive director of ISA Southern Chapter. I didn't put our logo on here, and I should have done that. I didn't want to make this too much of an advertisement for Southern Chapter, but I just want to mention real quick for those of you that are arborists, you're in the field, practicing in the field of arboriculture. If you're not a member of Southern Chapter, you really should join. It's $30. It's the cheapest chapter out of all the ISA chapters. You don't have to be an ISA member. You can join our chapter without being an ISA member. We encourage you to do both. We don't want to sidestep ISA. But you can join the chapter, $30. If you just, all you got to do is go to our website, and the website's super easy. It's isasouthern.org, and I'll put that up. It's on the very last slide. So $30, what does that get you? Well, it gets you $100 discount to our conference. So that's a pretty good deal. You save more than 3 times your joining fee just in savings for the conference. And any other event that you attend, any other Southern Chapter event that you attend, I can pretty well guarantee you'll get that $30 back. So it's worth it. And plus it just plugs you into a great network of great people. So with that, I'm going to move on. And there we go. Okay. Just want to make sure we're going to get the slides moving here today. So yeah, we're here to talk about trees, right? We're going to talk about how they age, how they grow old and fall over, basically. I do a lot of expert work in courts and, courtrooms and just consulting with people and so forth. And, one of the things the courts and judges and all that, our legal system agrees on is that trees are natural living organisms that shed branches and fall over. It's just that's the most predictable thing we can say about trees. This is what they do, right? Um, and they're a natural system, much like humans, obviously very different. We don't want to make too many comparisons between the two. And I think the term is being anthropomorphic. We're very different, but we're both living organisms. And so we're going to talk about systems, things that are sort of independent events, but they all kind of work together to either achieve a goal or make certain things happen. Nature obviously is a system, right? And then we'll kind of zoom into just trees as a system. Trees kind of have, one individual tree has many different parts that all work together. So a tree is a system in and of itself. And then we're going to kind of talk about when things go wrong, when we have system failure, when the system kind of breaks down. Because when we have a system, the other parts, a lot of these parts are all working together. And if one part doesn't live up to those expectations or doesn't perform, it can disrupt all the other parts of the system. So we're going to talk about some of that when it comes to trees and how things can go wrong, I guess. All right. So, hey, we start with the real basics here, right? We know that trees can get to be very old. I think this is bristlecone pine. Um, I don't know for sure, but it's like one of the longest living organisms on the planet, or longest living trees, I guess. They're a couple thousand years old, very, very, very old, right? Um, but we also know that not all trees do that. Some trees barely make it past this stage. They may germinate from a seed or pop out as a sprout from a stump. But their surroundings or something just isn't right, and the system fails. Maybe there isn't enough sunlight, they don't produce enough energy, something goes amiss. So old trees, young trees, that's pretty typical. We know that if we look at a larger system, if you will, a forest, that a forest can be comprised of some trees where their individual system is still working pretty good. They do great. But yet there are lots of other trees within that forest that are either dying or dead, but they're part of the greater system, that forest system. And so we're very familiar with that when we go out in the woods, when we go out in the forest. But it's true in urban settings as well. Now, those of us that live in urban areas, we're not as smart. So sometimes we have to have people tell us, hey, this is a dead tree, right? I don't know how much humor there is in this, kind of sad to me, but that's the way it is. Sometimes people do this, I guess, as a reminder to the city agency, hey, get rid of this tree. So but the point here is that even in a city, even in a dense urban area or a small town, the trees that we plant to make our community more attractive or reap all the other benefits that trees provide, energy savings, stormwater reduction, all these technical benefits. Those trees that are growing in that community are part of a system as well, or they create a system. They are functioning together. They affect each other. They affect the urban system, whether it's temperature. We know that greener communities have less of the urban heat island effect. Large cities without trees, temperatures are several degrees than surrounding areas. And it's primarily because of reflective surfaces or the cooling effect of trees and tree canopy. Trees with large canopies provide more benefits. So again, just like the natural forest, the urban forest is a system as well. Now, you know, we got a lot of people doing a lot of research on these urban systems. We've been doing research on natural forests for years, and still a lot that we have to learn, but we have some ideas about how we manage some of those systems, those forest systems, to either promote certain types of habitat for wildlife or watershed protection, whatever it is. We look at different harvesting techniques. We look at a lot of different things. And it's the same thing with the urban setting. We're doing research to see, how long does it take to create a canopy, based on some new plantings and efforts. How big of a space does a tree need? What's the soil volume needed for a tree? How do the number of trees and the amount of canopy affect some of these temperatures that we were talking about? So a lot of research going on in these urban systems as well. All right. So another thing that we think about is the human body as a system. I mentioned that trees are like people in that we're both living organisms, right? So, if we kind of start to introduce some of these concepts that Alex Shigo brought to us back in the 70s and 80s. If you're not familiar with Alex Shigo, if you're younger, man, look him up. He's the godfather, right, for a lot of arboriculture and tree research. But he just had some great concepts and foundations that he brought to us and helped us to understand. So when he talked about trees and he talks about a system, he talked about, and you can see the quote here: a system is a collection of things. Just like I mentioned earlier, this collection of things work together to create some goal or objective. Okay. And so I have an image here of a human body. Human body, we have a system that circulates our blood. We have a separate system that circulates electricity. These are our nerve impulses and nerves that make muscles move and so forth, that affect our muscular system. We have a skeletal system that physically supports our body. We have a digestive system, a respiratory system, so we can bring oxygen in. So lots of different systems or parts and things that work together to make the human system, the body, function and work, right? Just like trees. Trees have different parts and functions that work together as well. But let's think of trees for just a second in terms of numbers of trees and all of these trees living in an area that I mentioned earlier. We'll just call it a forest. We have trees in that forest. We have herbaceous plants in that forest. We have mammals. We have reptiles. We have birds. We have soil bacteria and biota and all kinds of things that are happening in the soil. A lot of people describe soil itself as a living organism that has this system of events that take place. So very intricate and very involved system and process to make this forest live. Now, if we think about trees in this forest process, we look at the number of trees. The trees are really kind of a minor component when it comes to the number of trees. We could have billions of bacteria in soil, billions or millions of little microorganisms, but really maybe only a few hundred trees on a given acre of ground. So from a number standpoint, trees aren't that big of a player. But on a volume basis, if we look at biomass, they're huge. They're absolutely huge. Lots of biomass. So trees, even though we can look at numbers in different ways, numbers of trees or numbers of pounds of biomass, we know that without trees, that forest system just kind of breaks down. And it's hard to take a piece of land and convert it from forest and make it grassland and have it stay that way. Nature has a way of kind of reverting it to, without disturbance, reverting it to whatever the natural state was or should be. So some of these systems are very strong. Now, let's dial in now a little bit and start looking at just a tree as a system. And I apologize for the artwork. Yes, it's very outdated. It's kind of out of focus on purpose because we know that trees don't look like this, right? We know that their canopy isn't perfectly rounded unless some uneducated arborist did some pruning. We know that the root system doesn't look like this. This is a model that simply shows that trees have lots of parts. They have roots, they have root hairs, they have structural roots, they have buttress roots, they have a main trunk. The trunk has bark. The bark provides some protection. They have branches, they have twigs, they have leaves. These leaves function to provide energy to the rest of the tree. A very intricate system. They produce fruit so that they can reproduce. You got to have a way to kind of keep things going, right? So a individual tree can be considered a system as well. All right. So if we go back to our buddy Alex Shigo, I had the honor, the pleasure of knowing him when I was in college. When I was a graduate student, I was one of the students that would cut up all these tree pieces, these chunks of wood. He was doing some research at University of Missouri with a guy by the name of Dr. Al McGinnis. And I was the grad student going out and cutting some of these chunks of wood. And Dr. Shigo, I only knew him as, a guy, some researcher. I had no idea his stature in the world of forestry and arboriculture. But as I got older, it was like, wow, I learned who this man was. And then I actually had him, he was the opposing expert on a lawsuit that I was involved in. So that had me shaking in my boots a little bit. But it was fun, got a chance to know him and meet him through the years. And what a great guy and what an impact on our industry. I think these two books are still available. I don't know, his family was still publishing some of this material, but I'm sure if you go to something like Amazon or somewhere, you can find these. These two books should be in every arborist or forester's library. One is called Modern Arboriculture, and the other is called A New Tree Biology. You can see that Alex was big on one of his phrases, his catchphrases: touch trees. You can't learn until you go out and you touch it. So just huge, standard setting, life changing ideas about trees and how they grow. So I would really encourage you to get into some of Alex's work. We'll talk about some of it as we go along here, but I wanted to make sure that you were aware of him and aware of his work. So I'm going to back up real quick for something, because one of the things as I got older and I had the pleasure of hearing Alex at workshops and conferences, Alex loved to use the word system. He was huge on the word system and talking about trees as a system. In fact, when he said the word, for those of you that have ever heard him speak, he would talk about trees as a system. and he would draw out the M at the end of the word. I think so that people would stick in their head this idea of system. The trees are a system. So I realize I'm doing the same thing, but that's the idea. Okay. Trees are this intricate system. And like I said earlier, when one little part of that system fails, it can create a failure in the whole system. Sometimes it doesn't take much. Now, trees are pretty resilient. We know that they can generate response growth. Those of you that are arborists or understand those terms, and we'll talk about some of that later. But in some cases, one little thing can bring the whole system down. All right. Same with computers. I am not a computer wizard, and fortunately, we don't see this as much as we used to in the past, but man, I remember the early days of computers. I used to see this on my screen all the time, and there was nothing that could instill panic more, right? System failure. So, you know, a lot of times this idea of old mature trees or people, old people, old age, sometimes and if you look at old records, a lot of just from maybe 80 to 100 years ago, if you look at records, death certificates, or just, you know, um, records at cemeteries, and, they say cause of death, and they say old age or consumption, or, they had these weird little phrases. And, the reality is we really don't die of old age. It's that a part of our system just begins not functioning well. Um, the cells don't divide as regularly as they would, so we're not replenishing and creating new cells in various parts of our bodies, or some of the parts of our bodies just kind of wear out. Some of the muscle tissue, heart muscle tissue in particular, and vascular system just doesn't stay as elastic, and we start to see some issues. And these are things that I'm learning quickly about as I get older. So, this the term that we use, a lot of times is not really accurate. Oh, they died of old age, or that tree is over mature. It just died from being over mature. It's really not accurate, right? It's the same thing with people. They don't really die of old age. Now, the cool thing about trees that's very different than people, the functioning part of trees, a lot of us know about the cambium, and how the cambium is where new tissue is generated. It's meristematic tissue that creates new stuff. And that new stuff is usually cells that create vascular system. Trees typically operate with very, very young vascular tissue. Xylem and phloem is created every year in most species of trees. And so that vascular system, unlike people, stays very young. All right. So what typically limits trees is not that the cell tissue begins to degrade, because old cell tissue in trees just becomes wood, right? The xylem, or it becomes old bark that just sloughs off, or old leaves or needles that fall off. Typically, the growing part of trees is very new. So the limiting factor with trees typically simply becomes size. It's a size issue. And physics is a lot of times the thing that will begin to degrade trees and cause them to slow down. Okay. They just simply, and a lot of it has to do with water transport. We're going to focus on water transport for a little bit. A lot of trees just simply can't get the water up to the top of the tree. It's pretty straightforward stuff. Um, even after this stuff that we're going to talk about, and even after some of the material that I read to prepare this material, I I still kind of scratch my head and, like, how does a tree get water 120 feet into the air? It's pretty crazy. Um, and we know that as trees get older, they don't do that very well. And they begin, as long as other parts of the system are functioning, as trees age and as they become less able to move water to the tips and the tops of the tree, they begin to die back. And a lot of times it's from the top down. Now I realize there's a lot of different ways for this to happen, but this is fairly typical. They die from the top down. And eventually that material that is dying back kind of falls off. It begins to decay and fall off. And a lot of us use the word retrenchment. The trees are becoming shorter, and yet their trunks, may be a little wider. And by lowering their stature, it's actually turned out, whether they did it on purpose or not, I don't know. I don't know if you can see the air quotes. I don't know if you can see my image, but you know, it if whether it's on purpose, it's just turned out to be a great survival mechanism, because as they get older, maybe the root system is declining as well. And if they stayed 100 feet tall, the wind would have a better opportunity to push them over. But as they get shorter and less, they have less height, they're harder to push over. So this sort of becomes a built-in survival mechanism. They don't look very pretty. This is not something we want lining our public streets. This is where we have to step in and make some decisions about safety and so on. But in terms of the length of lifespan for the tree, some people would look at this tree and say, oh, well, that's over mature. It doesn't have long to go. Well, we know that if this was an oak in a lot of settings, and it was a 120-year-old oak tree, a really old tree, a century tree, there's a good chance it could live 200-300 years more. So, just because trees have gone into this state doesn't mean that they're near death. They're just going to look really different. They're going to serve our purpose as humans. They're going to serve our purpose less. So we make decisions to remove them. Now, again, I'm not making a point that, oh, we should leave big old trees, because, safety is important. We're just from a biological standpoint, we know that trees like this could continue to live for a long, long time. Even after they just start completely falling apart, there may only be a few twigs that are producing new foliage, but it's survival. The tree is continuing to survive. It may not be growing, but it continues to survive. All right. This is the model. So here's what's going on that slows them down. If I back up a little bit, here's what's going on that slows them down to keep the water from being able to get up to the top of the tree. All right. And it's this simple little process in trees. Some people call it capillary action. There's a lot of different technical terms. I'm not a physicist, but the idea, we know that water molecules tend to be sticky, right? They stick to each other and they stick to adjacent surfaces, whether it's a glass tube. We know that we can stick a pipette down into a beaker of water, and the water in that little pipette is going to rise higher than it does in the surrounding area. Now, part of that is the pressure of the surrounding water pushing it a little bit, but part of it is this stickiness that the water literally starts climbing the walls, right? Now, that's limited, of course, by gravity, because gravity is going to say, no, you can't come up here, and it's going to keep pushing it down. So this idea of water naturally moving up a tube is what trees rely on. It's one of the basic foundations. Now, rather than thinking of a tube like this, let's think of a tube that is super, super small diameter. And the idea is that the smaller the diameter, the higher the water will climb. As we reduce the size of that tube, the water can climb higher. Now, let's now shift our thought to xylem in a tree, right? You know, we know that the cambium right underneath the bark produces a new layer, or should produce a new layer of xylem towards the inside of the tree every year. And that xylem is what's moving water from the soil up into the upper reaches of the tree. All right. They're nanometer diameter tubes. They're extremely small, and they're all kind of mashed together. They're they become part of this vascular system in the tree, the xylem. Now imagine that as that as that xylem tube moves up the tree, or is formed in the upper parts of the tree, it gets smaller and smaller in diameter. The diameter of the xylem tube near the base of the tree is bigger than the diameter of a xylem tube as it gets up near the top of the tree into a small twig. And it gets even smaller when it reaches the petiole of the leaf, and even smaller as it enters the leaf itself. As the xylem gets into the leaf, it's now extremely small, but there's millions of them. And so they're all working to stick to these little tubes and climb and move their way up. All right. Now, we also know that because water cells are very sticky, as a water cell evaporates from the surface of a leaf, it tends to replace itself. It's pulling another one up the tube as well. So all of this pulling and pushing and stickiness works to help water move up these tubes. Okay. But there's a limit, right? Here's some diagrams depending on how detailed you want to get. Down here at the bottom, this is the water. These are the water molecules being, moved into the xylem in the root tissue. Okay. It moves up through the trunk, through the xylem that has been formed in the trunk, and moves all the way up into the xylem that is actually inside of the leaves in the tree. All right. This adhesion is sticking it to the walls of the xylem, and it's also, they're sticking to each other. So like I mentioned earlier, as a water molecule evaporates or transpires into the atmosphere, it kind of pulls another one along. So it's just a crazy, crazy system. Okay. But again, we kind of know there's some limitations, right? This is a really goofy picture. People really scratch their head on this one. This is a project I was involved in years ago at a Washington University here in St. Louis. This alley of pin oaks was about ready to be removed for new parking garages. Kind of a sad deal. These trees were older and were rapidly declining, but still sad to see them go. But one of the professors at the university got this big grant and said, hey, let's start pulling these trees apart and looking at things. So we hired one of these companies with these hydrovacs. We just started removing the dirt. We wanted to see what the root system looked like. So pretty crazy stuff, right? Obviously these aren't the fine hair roots. Those probably got sucked up in the hydrovac. But these are a lot of the support roots and a lot of the vessels that are used to transport water up into the tree. Okay. And if they're not functioning well, that leads to water loss and decline in the top of the tree, as we were talking about. So just like with anything in life, with a system and pieces of this system having to all work together, a lot of it, a lot of it's a numbers game. The more things you have, the more um, um, the more chance there is of one of those things going wrong, right? Um, it's what insurance deals with. Insurance knows that the more chances there are of something to happen, um, the more events there are, the more likelihood there is of an event happening. And I know that's sort of not making sense, but it's a game of chance. You know, if we're trying to roll a four, if we roll just one dice, the likelihood of rolling a four on that dice is, how many faces are there on a dice? Six, 1 out of 6. But if we roll 100 of them, now we're increasing our chances that any one of those could be a four. That might be our good event. Well, let's say rolling a four is a bad event. Let's say rolling a four is equivalent to, hey, these cells have died, or these cells are not regenerating because they're not getting the moisture they need. The chance of that bad thing happening is very real in a tree. Now, the other thing that chance plays a role in is what we call catastrophic events. A lightning strike, what's the likelihood of a tree getting hit by lightning? It's not very high, right? What's the likelihood of trees being killed by an invasive pest? Well, before we went on the air, Neil and I were talking about, some of these invasive pests that are wreaking havoc. We all know about emerald ash borer. Here's a shot of a street in Ohio, the before and after of emerald ash borer moving in. So, these catastrophic events can create havoc and create quick loss of lots of trees. So it could be this catastrophic event, or it could be a series of events that would lead to a system failure. And that those series of events can be related to the needs that a tree has. We know there's some very basic needs that we have to survive. Same with trees. They need sunlight. They got to photosynthesize to create their energy, right? They need water. They need water so that cell function can carry on in a normal way. They need nutrients. As they absorb water from the soil, they're also absorbing nutrients, macronutrients, micronutrients, all of these things that keep the system running. They need oxygen. We always think of trees as, oh, well, they absorb CO2 and they give us oxygen, but they also burn a little bit of oxygen or need oxygen to create new cells. This process of cell division takes a little bit of energy and respiration, and there's some usage of oxygen. So if we deplete trees of oxygen, particularly the root system, we have a problem, right? And trees also need physical space. We know that as we restrict available root area, we're going to limit the size of that mature tree. James Urban, in his book Up by Roots, kind of documents a lot of that relationship between available root volume and size of the mature tree, which could correlate then directly to the length of time we might have a healthy tree. There's some studies that show that a typical urban tree has a lifespan of about 7 years. That's pretty sad. Hopefully our management and culture and ability to care for urban trees, will increase that number. But left to their own devices, we know that a tree stuck in a 4x4 vault in a sidewalk that doesn't receive any attention isn't going to live that long, right? Okay. So we know that trees have these needs. If any of those needs are limited, it's going to reduce the likelihood of the tree being able to do, what it needs to do to survive. It's got to grow. Even in that retrenchment phase, even though it's not growing much, it still has to try to at least remotely remain upright. Trees got to grow and reach sunlight, and they got to be able to defend themselves. Some of the energy that they create, some trees put a lot of that energy into growth. They grow fast. Willows, poplars, these are trees that grow fast, but they don't defend themselves very well. Trees that grow slower, maybe oaks, hickories, some of those types of trees, they grow a little slower because they're putting a lot of their energy into defense mechanisms, whether that defense is physical defense or whether it's chemical defense against insects and disease and so forth, decay. It takes energy for those defense mechanisms to kick in. So if we limit some of those tree needs, we're going to limit the tree's ability to do these three things that it needs to continue to survive. So, we've kind of already gone over some of this in terms of structure and development of trees. We talked about the cambium. These are some slides. If any of you have been through a track course, you've probably seen these diagrams. These are some of the slides from track, the tree risk assessment qualification. We know that trees had cambium. This is the active zone of cell division and growth. In fact, it's the only real active zone of cell division and growth in a tree. It's right under the bark, and it produces cells that will increase the bark, the size of the bark or thickness of the bark. We call those cells phloem. That's part of the vascular system that brings the sugars and the starches back down into the other parts of the tree from the leaves. And then to the inside, we know they produce xylem. And the first year or so of xylem this is the vascular system that is carrying the water and nutrients from the roots up into the tree. And as that water moves through the tree, especially when we get into the smaller diameter parts of the tree and into the leaf tissue, it acts as a cooling mechanism as well. As that water evaporates from the surface of the leaf, there's a cooling effect. There's a net cooling. Again, chemistry and physics, don't ask me to go there, but it's a net cooling effect, all right? All part of this system. And so, again, we're not going to go into a ton of detail here, but there are different types of xylem cells or different types of the structure of the xylem. We have cellulose, which is stringy and allows cells to move. These are cells that move. And then we have lignin that provides stiffness and it provides strength under load. So when gravity tries to mash a tree into the ground and push on it, those cells become compressed, but the lignin adds strength so that they can't be mashed into the ground. All right. Cellulose provides strength under tension as the tree moves back and forth and twigs and the trunk is stretched, as it leans. The cellulose, it's like a rubber band. It'll stretch but it won't break, and it will pull itself back up straight. Kind of has a little bit of a memory. So it's this combination of the cellulose being flexible and the lignin being rigid that provides the perfect combination for trees. They can move, but not too much. If they were all stiff and structure, lignin type structure, they become brittle. They could snap. And we see some trees that do that. As they decay, the cellulose decays first. All we're left with is lignin, and the tree snaps. And then there are some types of decay that do just the opposite. They take the lignin away, but they leave the cellulose. So now the tree becomes very soft and spongy and is weaker, but at least it's still moving a little bit. And that movement may actually trigger new cells to grow. We call that response growth, and we'll kind of look at that. We've already talked about retrenchment. I kind of jumped ahead on the retrenchment. Um, we talked about long-lived and short-lived trees. So I was just talking about response growth and the idea that when a tree moves, when the wind blows, the cells in that tree, when the trunk bends or a branch bends, the cells on one side are stretched, they're under tension, and the cells on the other side are compressed, they're under compression. And trees will respond to this. Trees will develop new tissue and additional tissue to help the tree respond to future stress. So the more that a tree, if a tree's out open grown in a field, it's going to get wind all the time. And it's going to, and again, air quotes, learn. It's going to respond, is the right term. It's going to respond by developing extra tissue. The trunk's going to be extra big and it's going to have a lot of taper so that over time, the tree knows it will be able to survive that open grown wind site impact. Now, a tree like a lodgepole pine that's growing with maybe thousands of other neighbors on an acre of ground, very skinny, very tall. They don't move much because they're protected by all their neighbors. But if we remove a lot of the other trees and we leave one of those, if it's new exposure to wind, that tree doesn't have the tension. It hasn't developed response growth that will help it tolerate those wind loads. Okay. So whoops. Why are we going backwards? Let's go forward, shall we? All right. I'll figure this out. All right. So here's an example of response growth. This is compression wood on the bottom side of a branch. Here's tension wood on the top side of a branch. So trees will respond to the situation based on whether cells are being stretched or cells are being compressed. It's how they grow taper. As the trunk moves in all directions over the years, it's going to develop a lot of growth near the base and develop taper, which helps it stand up. Trees also develop woundwood, which is a response to cutting through the cambium. So they grow new tissue to cover wounds or add strength to wounds. Okay. Here's some woundwood that is adding tremendous strength to this tree. Okay. All right. Without woundwood, if decay becomes prevalent, decay just starts to weaken the tree. And we have a lot of different types of decay: white rot, brown rot, soft rot. And this decay just weakens away at the structural strength of the tree. And if it's eating away at the xylem on the inside of the tree's going to become weaker. It's going to lose strength, especially if some of that decay, there are some types of decay that will eat at the outside of the tree, sapwood decay, and the tree loses a lot of strength. Okay. So a lot of different types of decay that can reduce the strength of tree. And again, it depends on where it's located. Heartwood decay, not so bad, but sapwood decay, that's a big problem. If we lose sapwood, if we lose strength in the outer edges of the tree can lose strength very, very quickly. A good example of sapwood decay that you all might be familiar with, arborists and foresters, is hypoxylon. This is the white or tan or grayish, chalky looking decay that occurs and the bark sloughs off, and it eats away at the sapwood of a tree and can quickly reduce the strength of a branch or a trunk. And of course, root decay is a huge issue because roots, we know, provide physical support as well. And if those roots decay, we got a problem. But a lot of this decay is hidden. We have to use some tools and techniques to try to look for that type of decay. All right. So We know that trees that are long livers tend to compartmentalize well, meaning they can cover over or they can resist decay and block decay from spreading through the tree. Trees that do this well live a long time. Trees that don't do this well live a fairly short amount of time. Okay. So, the question a lot of times that we get is, so how much decay can a tree have? How much is too much? And we're kind of learning this. We're not really there yet. There are some people that are publishing tables about the percent of heartwood decay in certain species and what percent strength loss that creates. I haven't relied on them yet, but there are a lot of people that do, and it's just some of the research that is being done these days. So we know that as a tree decays, it now loses strength, and things like gravity are pushing on the tree, trying to pull it down. Wind blows on it. Wind is a nasty one because this is a force that is dynamic. It changes speed, it changes direction, and can create a lot of problems. We're not going to go into a lot of the detail here because we're just about out of time. But this is the physics behind the force of pushing on a tree compared to the length of the lever arm. How tall and skinny is this tree? Where's the center of the canopy? And that's going to affect the energy that builds up down here at the base of the tree or at the base of every branch attachment. If we have a long, skinny branch, arborists know the term lion tailing. If we lion tail that branch and we remove all the branches except for the leaves and branches out on the tip, we create a branch with a long lever arm. And if the wind pushes on that branch, there's more energy now that builds up where that branch is attached to its parent stem. And we increase the likelihood of failure of that branch. So all of these forces, all of these things that are acting on a tree can bring about failure. So when we look at how trees age, how they get old, we talked about system failure, and that's usually related to water movement. We have catastrophic failure, which there's not a whole lot we can do about that. We might learn about invasive pests and learn ways to control them or repel them, but catastrophic events like lightning and so forth, not much we can do about. And then trees also fail based on strength and structural issues and weakening of tissue over time. So this is the way they kind of end. This is the way they come apart. I know a lot of that is very basic material, but unfortunately we only have an hour, and I always like to have 2 or 3 hours because I could go on forever. The one thing that I want to remind you about, just another quick advertisement for ISA Southern Chapter. Go to the website and join Southern Chapter. It's $30. It's it's an honest thing. It's a great investment if you're an arborist. Another great investment is taking the time to attend our annual conference. It's coming up March 24th through 26th in Little Rock, Arkansas. We're excited to be in Little Rock this year. You can go to our website and you'll find information about the conference. That is about all of the material that I have. And I'm looking to see if there were some questions. I saw Rachel had something about, could you post that exposed root picture on Bugwood? It's great. I will figure out how to do that. Or Rachel, if you just want to reach me, if you go to the ISA Southern website, you can send me an email that way, and I'll share the picture with you. But I'll figure out how to get that out there. Make sure that it looks like a lot of you have typed your name and certified arborist number in. Those of you that registered, I think your certified arborist number is there as well. But I think Katie likes to make sure that your name is listed and your number so that she gets all of that data. and she will see to it that you get your ISA CEUs. So that is all that I have, folks.
Thank you so much, Skip. I do have a couple questions for you, but I did just
Sure.
want to say, anyone, if you have to jump off now, that is completely fine. I should have your information through the chat and the registration. Um, but I do have a couple questions that were sent to me through direct message.
Sure.
Um, are there any treatments an arborist can use to treat an older, maybe declining tree?
Wow. Um, the honest answer is there's really nothing you can do to a tree to slow down aging. I mean, it just is. It just happens. Now, the best thing that you can do for older declining trees is that the biggest issue typically with older declining trees is root system. We talked about they're going to be limited physically by being able to move water up to the top of the tree. But even as that happens and you start to get some dieback and some branch dieback in older trees, you can prune those out, keep the tree around, but take care of that root system. Mulching is a great way to do that. Organic mulches, either shredded wood and bark or ground up leaves. We don't. I don't rake leaves at home anymore. I run the blower around a little bit. I'm one of those obnoxious noise makers every fall. I suck them up, I run them through the grinder, but then I redistribute them over all my beds. Um, I have a very small strip of turf. I got rid of the majority of my turf, and I put some little strips in the turf, and I put compost down each year to get compost into the roots of the turf. But for older trees, root system, paying attention to the root system. Mulching is a big thing. Fertilizing or nutritional additions are a great tool. Soil, injecting fertilizer into the soil. A lot of experts will tell you that's the best way to fertilize trees. But I'm not big on over fertilizing with a lot of nitrogen. It's typically micronutrient issues. So soil testing is a good idea to see what you need to apply, or get hold of an arborist, have them come out, look at your tree, and make some recommendations.
And I've got a few more if you have time.
Sure, I'm all good as long as folks want to stick around. I'm here.
Okay. How can a city make the decision on removing or saving an older tree?
Ooh, um, by flipping a coin. I'm kind of joking here, but I'm not. Um, it's a tough one because an a person who is a municipal arborist, somebody who manages a population of trees that are owned by the city or on public property, they have to have many talents. They not only have to be a good arborist, a good tree person, they have to be a good communicator. They have to be able to know how to manage that system of trees to maximize the benefits, to have as many big trees and promote canopy and all the benefits of trees. But at the same time, they have to have the ability to assess and manage risk. As the pictures that I showed you, as great as it is to have big old trees around, if they're around where trees and property are located, we now have decisions about risk. And it's difficult. A lot of times there's controversy and politics involved in a decision to remove a tree. Um, I was a municipal arborist for the city of St. Louis, 100,000 street trees, about 500,000 or more park trees. It's a daunting job, and it's a thankless job because you have limited resources, you have a budget, and you got to do all these things with this limited budget. So I guess the best thing I could tell people, if they're not a municipal arborist, be very careful about pointing a finger at your city arborist and saying all they want to do is remove trees. I'm sure there's some that are more excessive than others, but most city arborists, they're tree lovers, they're tree huggers. They don't want to cut them down, but they have to manage risk. So it's a difficult one. And I know we have some municipal folks on here. The folks that I mentioned earlier, all three of them are municipal arborists. I work with municipal folks all the time.
Are there longevity differences between deciduous and coniferous trees?
Great question. As a general rule, man, I don't even know if this is true. I was going to say deciduous trees probably last longer, but a lot of the oldest trees are coniferous if you go out west. Um, there are, and I saw somebody ask a question, it might be the same person. Is there a chart that tells the longevity of trees? I don't have a resource for you, but I would be willing to bet if you did an internet search about, a chart for expected, lifespan of trees, there's got to be something out there. Again, generally we know that in the hardwood world, oaks, hickories, these tend to live longer than things like poplar and willow. And the faster a tree grows, the shorter its lifespan. That's a pretty good rule. And that creates a conundrum or a problem for somebody who wants to plant a shade tree in their backyard to shade their new deck, right? Well, I want something that's going to shade it fast. Well, you pretty much have to resign yourself that anything that you plant, you're probably not going to see the benefits from unless you do it when you're young. It's like investing money, you got to do it when you're young. So, we do this for the next generation. Okay.
And those are all the questions I have.
Okay.
Okay, thank you, Katie, and appreciate those of y'all that sent in questions. And if y'all want to follow up with Skip, I know he's told you just to visit the ISA Southern Chapter website, and they can submit those questions or requests to him directly.
Yeah, there's buttons all over that site that are, contact us, and that'll send me an email. Absolutely.
All right, well, that was a great presentation. And Skip, this is number 2 for you. We've had you on before, and you have an open invitation in the future. If you have some topics or information you want to get out to our audience, just let us know and we'll put you on our schedule.
I'll send you a list, Neil. Always happy to be here. Always
All
happy
right.
to be here.
Okay. Katie, we have a couple of slides I think we want to go through as we close out this webinar.
All righty, let me pull that up.
And while she's doing that, I want to thank everybody for
Whoop.
attending. We saw a lot, I think virtually everybody that signed in at the beginning stayed on through the end, which is a good indication of the great job Skip did. All right, well, this was the first webinar for 2024. We have our next speaker scheduled. You can put this on your calendars. You will receive a reminder from Katie a little bit later, but we're going to have on February 18th, Emily Swackhammer, who's with the Penn State Extension, and we're real glad to get her perspective here. She's going to talk about the Pennsylvania experience related to the spotted lanternfly. And for those of y'all that's still with us, Tennessee detected the spotted lanternfly in Nashville just last year. So it's here in our state, and we want to get prepared in responding to that. So we're wanting her to tell us some of the lessons learned from Pennsylvania. And then there's those of y'all from other surrounding states or beyond that may be worried about this invasive as well. So you really want to set aside some time to listen to her presentation, because we always can learn from those that have gone through the choppy waters that we're about to face with this pest. And once again, as a reminder, if you want to earn a ISA CEU from Emily's presentation. It's the same registration process, but there will be an added $10 fee. Just to be upfront with y'all on that change. Everybody else will be free.
A quick note, somebody just typed this in and I just looked and they're correct. February 18th is a Sunday.
Okay. You can tell that we put this together just quickly. Are you looking at the calendar now, Skip?
Yeah, it would be either the 15th or the 22nd, probably the 15th if you're staying middle of the month.
Third Thursday.
It's
Third
the
Thursday
15th.
would be February 15th.
Okay, well, I will plead guilty on this. We'll correct that. So
I'm glad I've never done that.
exactly. But okay, we'll make that change and pass that out to everybody. But thank you for catching that, whoever that was. We appreciate it.
That was Donna Fair that I saw.
Oh my
Thank you,
goodness,
Donna.
no, Donna, she does things by the book. Okay, Katie, do we have anything else we need to mention?
Let me go through here.
I know what I'm doing when this webinar ends.
I was just going to
Correct that
remind
slide.
everyone, if you need CEUs and did not enter your information during registration, feel free to email me.
Okay, super. Okay, well, that's it. Well, thank you, everybody, again, and you, Skip and Katie, and we'll see you next month.
Thank you, folks.